All right, so today we first finish the chapter 17, and then we'll start the new chapter, chapter 18. Okay. And for chapter 17, okay, so if you have any question, still you can type in the chat window. Okay. I would say most difficult part for the chapter 17 is kind of things design. Okay, so because there is a lot of small things. Okay, so there are some kind of lot of consideration, lot of reaction involved. Okay, so here I try to list all of them kind of together. Okay, so first, it's kind of attached group. Depending kind of also para director or kind of meta director. That's what we already talked about kind of in the class on Friday. Okay, and also talk about kind of if you want to think it's kind of primary RQ benzene case. So you do it kind of the indirect way. Okay, first the free craft acylation followed by kind of reduction. Okay. And then the third one is kind of just keep in mind, okay, there's no direct kind of any the ES reaction for aniline. Okay, so last we already learned that kind of before. Okay, so because the aniline is kind of amine group. Okay, it's strong base and also nucleophile. Okay, and so have react with any kind of acid conditions. Okay, or some kind of any other kind of ES kind of reagent. Okay. So if you really want kind of do the reaction for the aniline case, so remember, okay, we learned kind of protected case with the acetyl chloride case, so acyl group, okay. All right. And then this reaction pretty much you don't need any reagent, okay, so pretty easy reaction, okay. All right, and then falling kind of you can do whatever the ES reaction, okay. All right, so once so assuming you put so this amide group is still kind of also pair directors. Okay, so assuming you put kind of the electron file on this kind of pair positions. Okay, and then you just kind of do the protection. Okay, so normally speaking, kind of potassium hydroxide okay, base. Okay, remove kind of the protect kind of the acid group. Okay, so that's give back kind of the amine. Okay. Yeah, so that's we learned kind of before. Okay, right, and the next kind of also protein group is kind of cyanate. Okay, sulfur sorry, so sulfonate. Okay, so sulfonate kind of pretty good kind of block the pair positions. Okay, and then you can put such a group onto also positions. Okay, so those the were learned before. Okay. And so the next kind of reversible kind of attach can be removed kind of the group is the nitro and also the amine. Okay, so what happens kind of here. Okay, so if you has some kind of nitrobenzene. Okay, all right, and then this one you can convert to kind of the aniline case, so amine group case, we do the reduction case, so reduction R. Okay, right, and then falling kind of you can do whatever we call the kind of the diacetyl reactions. Okay, some acid conditions. Okay, we can convert it's to kind of the diacetyl ion. Okay, and then we can do any the substitution reactions. Okay, so use the nucleophilic substitution reaction, or just kind of directly use the sodium boron hydride or some kind of the hyperphosphoric acid. Okay, so you can cleave off kind of the whole kind of the NH2 case, so sodium boron hydride. Okay, give back kind of benzene. Okay, this is kind of the pretty much, especially kind of bottom strategy kind of look like pretty much nothing reaction happened. Okay, so it's pretty cool kind of the application for this reaction, give you one example. Okay. All right. So for example, okay, so we try to make this kind of the also bromo chloro kind of the benzene. Okay. So from benzene. Okay. All right, so if you want to directly do kind of your bromination or chlorination, you find kind of it doesn't work, okay? Because both your chloro or bromo kind of also para director, okay? But now they kind of in the meta positions to each others, okay? So in this case, you can think about kind of use nitride and also the diazonium strategy, okay, to finish its conversion because the nitride groups kind of also meta directors, okay. All right, so pretty much the reaction what you can do is first, okay, we do nitration, okay. All right, so for example, we put it over here, nitration, okay. Right, and then falling case we this is kind of meta directors, okay. We can do chlorination, okay. All right, so no problem. You put kind of the para positions, okay. All right, and then falling kind of you have to try to find a way kind of remove this convert this nitro group into kind of bromine, okay. So we can use kind of diazonium kind of reactions, okay. So first kind of reduce the case, so reduce it kind of we use right, so the catalytic hydrogenation reaction conditions, okay. So but if you like, you can use also the iron with the HCl, or kind of the tin chloride with HCl, okay. So all these three conditions work, okay. So amine, okay, right, and then falling case, so we convert kind of diazonium, okay. All right, Cl here, okay, O plus, okay. Right, and then the final step, okay, okay, so this one, react with we call copper's kind of the bromide, okay, so CuBr, okay, so not Br2, okay, so only copper's one, okay, copper one, okay, and then that kind of replace kind of diazonium with kind of bromide, okay, kind of the DDR plot, okay, so that's the pretty useful strategy, okay. Right, and so next kind of interconversion of nitro also para director with kind of meta directors, okay. So that's if you one thing you want to synthesize kind of not on ideal positions, okay. So for example the group already on kind of benzene is kind of also para directors, but here also conditions kind of the meta that's up to kind of benzene, okay. So in this case, you can think about kind of use all these two, okay. Okay. So one we already learned kind of the nitro, okay. So and then you reduce kind of the aniline, okay, amine, okay. Another one is kind of you can converted the ketone, okay, carbonyl compound into kind of the alkyl group, okay. So ketone is kind of electron donating electron withdrawing group, okay, and then all meta directors, okay, but the alkyl group kind of the actinic group, okay, and also also para directors, okay. So that's pretty useful, okay. And there's one way can you do reverse case where you can convert the alkyl the benzene, okay, into kind of the benzoic acid, okay. So that you convert kind of also para director into kind of meta directors, okay. Right, so give you guys maybe one example, okay. Right, for example, we ask you kind of synthesis kind of this P nitro benzoic acid, okay, from the maybe any alkyl kind of benzene, okay. Right, so if it directly from alkyl group benzene, alkyl group kind of also para directors, okay, no problem, okay. But if you directly from kind of benzoic acid kind of the meta director cannot put kind of in nitro group, okay, positions, okay. So in this case, for this reaction, okay, so we'll do the kind of the nitration first, okay. All right. And then that's here also para director, no problem. Okay, you can put kind of here at para positions. Okay, right. And then following kind of here you can do the oxidation reactions. Okay, we use kind of potassium the permanganate. Okay, yeah, that's we learned kind of in this chapter. Okay. And so that think about it. Okay, so if final product kind of not idea kind of direct effect. Okay, so think about kind of the convert to kind of another the director. Okay, so also para to meta or kind of the meta to also para. Okay. Okay, and then last thing is kind of just keep in mind. Okay, so if there's kind of the electron weight group, okay, weight group, okay, so on the kind of bending ring, okay, so there's no free radical activation and also free radical acylation reactions. Okay, so now it's working. Okay, so what's that mean? Okay, so just give you guys kind of the one quick example. Okay. Right. So for example, kind of ask you kind of try to make this one should be kind of the acetyl the p nitro acetyl kind of bending okay, acetophenol okay should be called kind of. All right. So from kind of bending okay. All right. So if you take first look, okay, so this is two kind of the meta position to each other, okay, and then both kind of the meta directors, okay. So life should be looks like quite easy. Okay, you can put kind of nitro group one, kind of do that for the acylation, or kind of put kind of the acid group one, and then do the kind of nitration reactions. Okay, both kind of idea. Okay, but keep in mind. Okay, so for the acyl group, okay, free radical acylation, okay, so you have to kind of make sure there's no deacting group on the bending, okay, you can do it kind of free radical acylation, okay, but if you already have kind of the deacting group on the bending, okay, if you want to do kind of free radical acylation reactions, okay, so so that's not working, okay, because just showed here, okay. No kind of electron weight group attached to bending, okay, so can do any kind of free radical acylation or free radical acylation reactions. Okay. So that means kind of in any situations, okay, if you already find kind of the acyl or kind of the acyl group on the bending ring, okay, so you do the FC acylation first, okay, or FC kind of acylation first, okay, and then other reactions, okay. So that's keep in mind, okay, so if you have the acyl group on the bending, okay, so do this acyl group first, okay. Right. So in this case, for this, the reaction pretty easy, okay. We do the FC acylation reaction first, okay, and then we do the nitration, okay. So nitration reactions kind of okay, we kind of the final product, okay. A little bit more. So that's some small thing you have to think about it, okay. So all right, and then one of the most difficult type question in kind of the synthesis design of this chapter is kind of the tri-substitute bending, okay. So that's need a lot of analysis, okay. So quite time consuming, okay. Probably I want to put the tri-substitute bending kind of synthesis in the quiz 4, okay. But you probably will see kind of in exam the 2, okay. All right, tri-substitute, okay. So this is a very good example, okay. Right, as you kind of try to make it this the tri-substitute the bending from bending. Right. So quite often students kind of don't know where to start, okay, and then begin kind of the try kind of or kind of the ways, okay, to do it, okay. So that you can do the kind of we call it the systematic analysis, okay. So do it stepwise, kind of go backward, okay. So for example, okay, so for this tri-substitute, okay, we assuming already two substitute group already on the bending, okay. and then we try to put the third one, okay, to see whether it kind of get the ideal kind of the locations, okay. All right, for example, okay, so for this one, okay, so assuming we already have kind of BR and also this the RQ chain on the binding, okay, and then we see whether we can put kind of nitro group on kind of it, okay. Right, and then you find kind of for the RQ group kind of the disruptive situations, okay, so you have to find which ones kind of the higher kind of activating group, okay. So RQ kind of the weakly activating, and this one kind of weakly deactivating. So that means RQ group kind of boss, okay. If you want to the nitro group go kind of, it's also para positions, okay. So yeah. Right. So that means this reaction should work, okay, because targeting molecule kind of the go to kind of it's also positions, okay. So that's work, okay. Right. Another one, okay, so we can try kind of how bromine and also nitrate group on, okay, and then to see whether we can put the RQ group on, okay. All right, so we have kind of bromine and also the nitrate group, okay. And then that's the boss is the bromine, okay, because it's kind of weakly deactivated, is kind of strongly deactivated, okay. So this is the boss, okay. So the bromine is kind of also para deactors, okay. Once the substitute group goes is kind of also positions, okay. So part kind of block here, okay. But here you can see kind of this RQ chains kind of on its the meta positions, okay. So that means this route doesn't work, okay. Right, and then how about we have nitro and those the RQ chain, okay, and then whether we can put the BR on kind of the ideal positions, okay. So that's we just have to solve all the situations, okay. So yeah. Right, so here, okay, so the RQ group kind of the weakly activating, and then nitro group kind of the strongly deactivating. So the boss is kind of nitro group, okay. So that's determine kind of the bromine positions, okay. So the RQ group kind of also para deactors, okay. So once the bromine goes here, and then also here. But for targeting molecule, okay, so that's the bromine goes to kind of meta positions, okay. So that means kind of this synthesis route, okay, also cannot work, okay. So that's you do the backward, okay. All right, okay. So once we have these two, okay. So then we need to determine kind of we put on bromine first, or kind of put on kind of the kind of RQ chain first, okay. All right. So if you take first look, you find okay. So it looks like neither one's working, okay. If we put bromine on first, okay, bromine can also para directors, okay. So if one kind of put RQ chain on first, okay, so that's also para directors, okay. So no way you can put these two kind of into the meta positions, okay. So that's you have to use the strategy we just learned, okay. So change also para director to kind of the meta director, change the meta director to kind of also para directors, okay. Here, okay, you see here, okay. So we can do kind of isolation first, okay, and then after put the bromine on, okay, and then we try to kind of reduce it, kind of get the final kind of product, okay. All right. So what happened? Kind of we can do this way, okay. So here, okay, so this here the ketones kind of also meta directors, okay. No problem. You do bromination, okay. You can put here the bromine on kind of meta positions, okay. And then afterwards you do reduction, okay. Reduce kind of this RQ group into kind of RQ chain, no problem, okay. And then that's pretty easy, okay. So we can do kind of the free carbon acylation, okay. So just kind of from bending, okay. Okay, okay. So that's the how to do kind of backwards analysis, okay. Finish the analyze kind of all the possibility, okay, and then get kind of the idea kind of the tri-substitute product, okay. And here the kind of the oral synthesis route, okay. And actually kind of there's one more step, okay. So in the end, can do kind of nitration, okay, put the nitro group on kind of the also position to kind of bromine, okay. And so probably this Thursday we'll do a little bit of practice about kind of trisubstitute kind of benzene, okay. All right, okay, so that's we are done the chapter 17, okay. Before we move to kind of the chapter 18, okay, just the one thing kind of we have to decide when we have kind of before kind of we have to decide when we have kind of quiz 4, okay. So quiz 4 only carry the chapter 17, okay. So go to the pool, okay. All right. So just kind of make choice, okay. So you can have kind of we can have kind of the quiz 4 on kind of the Wednesday or kind of Thursday or Friday or latest time kind of Saturday, okay. So I don't want to put the quiz 4 on Monday, okay, because they are quite busy during kind of the week, okay. So like quiz 3, okay, pretty much take much long time kind of go through all the kind of the quiz, okay. So so if we can have kind of quiz by Saturday, okay, so probably I have some time kind of finish go through it kind of on Sunday, okay. So all right, so just make choice, okay. So which day do you want to kind of have a quiz for, okay? Wednesday, Thursday, Friday, or Saturday, okay. So if you want more time preparation, okay, so my suggestion kind of maybe Friday, Thursday, or kind of the Saturday, okay. All right, and then give you the 3 seconds, okay. All right, please vote, okay. All right, 3, 2, and 1. All right. All right, so looks like most students kind of voted Saturday, okay. So 9 p.m. to kind of the 12, okay. Okay, so in this case we'll have kind of the quiz 4 on Saturday evening, okay. In Saturday evening, okay. So if you have a kind of conflict schedule, okay, so please let me know, okay. So I can do a little bit of kind of adjustment, okay, for you guys. All right, so quiz 4 will be on Saturday, okay. And in this case, probably on Thursday, okay, we also do a little bit of practice, okay. So in the discussion, how you guys can prepare quiz 4, okay. Do we ever worry about yes, okay, so that's the right question, okay. So so there's kind of possibility you can also put a nitride group on here, okay. So that's true, okay. So we expect the next exam, okay. So the next exam kind of exam 2 will be next week, okay. So probably the on Friday or maybe kind of in the weekend, okay. yeah, don't drink on Saturday, okay. But after quiz you can drink, okay. Earlier, okay. So it's possible, okay. Possible, okay. So but Saturday actually kind of we can I can open longer time, okay, because there's pretty much no class, okay. So I will think about it, okay. All right, any question about kind of quiz 4 or kind of chapter 17? All right, okay, so looks like no question, okay, that's good, okay. Okay, so now we'll start kind of a new chapter, okay, chapter 18, okay. So chapter 18 and 19 and also 20 all about carbonyl reactions, okay. And this guy, okay. So pretty much I don't want to open kind of the for whole Saturday, okay. So reason for that kind of some student kind of maybe transfer the quiz the material out, okay. So if it's open too long time, okay. So there are some kind of possibility for the cheating, okay. All right, so yeah, for the chapter 18, we will learn about kind of addition reaction to the carbonyl compound. Okay, so yeah, mainly kind of aldehyde ketone. Okay, yeah, and chapter 19, we will learn some kind of reaction about the substitution reaction of the carbonyl compound. Okay, mainly about kind of capsaicin, okay, ester, and also acid anhydride, and also the acid chloride, and also maybe some kind of the nitrate compound. Okay. And so for chapter 20, okay, we will learn something of the alpha carbon chemistry of carbonyl compound. Okay, so pretty much we spend kind of 3 chapters. Okay, learn kind of the carbonyl reactions. Okay. All right, so like I said, kind of this chapter pretty much we all just learn kind of reaction about aldehyde ketone. Okay, so aldehyde ketone, you guys should remember it. Okay, so for the ketone, you have kind of 2 alkyl group case, just the connect to kind of carbonyl group case. And then for the aldehyde case, so 1 alkyl group, 1 hydrogen case. And so for the reactions, the chapter we said kind of the addition reactions. Okay, so for the nucleophile. Okay, so actually kind of also called kind of nucleophilic addition reactions. Okay, nucleophile will attack kind of the only carbonyl carbons. Okay, reason for that kind of this one has kind of the partial positive charge, and then oxygen has kind of partial the negative charge. Okay, so nucleophile normally just kind of the rich with electrons. Okay, like attack kind of the carbonyl carbons. Okay. And also because the aldehyde ketone kind of is somehow kind of planar structure. Okay, so the sp2 hybridized. Okay, so the triangle. So in this case the nucleophile can attack from either top of it's carbonyl carbon or from a bottom of carbonyl carbons. Okay. Right. Okay, so here's kind of the general reaction for these chapters. Okay. So pretty much just use this indicate kind of aldehyde ketone. Okay. And remember, okay, so we have kind of a positive charge on the carbon, negative charge on oxygen. Okay. Right, and then you react with the nucleophile. Okay, so this nucleophile can be a negative charge species. Okay, or some maybe kind of neutral nucleophile. Okay, so so neutral nucleophile normally some kind of has hydrogen on it. Okay. All right, and so this step we call kind of addition. Okay, so pretty much a nucleophile attack kind of carbonyl carbon, open CO bond. Okay, and then the oxygen pick up the hydrogens. Okay. So pretty straightforward. Okay. And so let's see, we call it kind of addition. Okay. So about like half of the reaction we will learn kind of the chapter the 11 chapter 18 will just kind of stop at this stage. Okay. But couple reaction will move kind of one more step. Okay. So we call it kind of the elimination. Okay. So what happens kind of instead kind of you stop at kind of alcohol stage. Okay. So the alcohol pick up some kind of the hydrogen from the solvent. Okay, become kind of water. Okay. And then meanwhile, okay, so the nucleophile, okay, has some kind of the lone pair electrons on it. Okay. So in this case, the lone pair electrons can on the nucleophile, okay, can further attack kind of the carbonyl carbon. Okay. And then kick off the water. Okay, so pretty much kind of somehow like the elimination reactions. Okay, and then you generate something like this. Okay, so that's the we call the elimination. Okay. So we'll learn probably 2 reactions. Okay, two. Okay. Addition followed by elimination. Okay. All right, and then there's one reaction kind of extremely kind of hard. Okay, so won't stop up here. Okay, we'll do the kind of second addition. Okay, and add the nucleophile on. Okay, add second nucleophile on. Okay, and then eventually you get something like this. Okay. you have kind of two nucleophile attack kind of center carbon, okay. So that's here the overall general reaction for these chapters, okay. So most reaction will stop at kind of just the addition step, okay. Two reaction probably do kind of addition followed by elimination. One reaction do addition, elimination followed by addition, okay. So that's here we will learn kind of one by one, okay. And here just kind of the general comparison of both we learn kind of electrophilic addition, and also here we also learn kind of nucleophilic addition, okay. So what's the difference, okay? So for the chapter we learn this reaction, we learn this chapter. It's kind of the attacking species kind of nucleophile, okay, right? Attack here and open the CO bond, okay. So that's why we call them kind of someone asked questions, okay. So depend on the nucleophile. Yeah, that's right, okay. So it really depends on the nucleophile, okay. So some nucleophile stop at kind of first stage, okay. Some nucleophile push to second stage, okay. And then there's one nucleophile, okay, push further, okay. So okay, you kind of two step, okay. So we'll learn kind of one by one, okay. Yeah. Right. So that's the reaction we learn these chapters, okay. So that's this here, okay. We call kind of nucleophilic addition, okay. And then in chapter 11 we learn the reaction called kind of electrophilic addition, okay. The attacking space is actually kind of the electron file, okay. So so remember, okay. So in that chapter we have kind of the CC bond, okay. And then the electron file, okay. So CC bond rich with electrons, okay. Yeah, something like this, okay. So that's like the mechanism 1, 2, 3, okay. So all kind of follow this path, okay. So that's something just little bit keep in mind, okay. So between all these difference, okay. And the good thing for this chapter, okay, because like I said, kind of the whole already have ketones kind of planar structures, okay. So the nucleophile can attack from top or from bottom, okay. So that means kind of no serial selectivity, okay. No serial selectivity, okay. You don't need to worry about kind of the anti-addition or sin addition, whatever, okay. Another good thing for you guys, kind of there's also no nuclear residual selectivity, no residual selectivity, okay. So for the kind of arcane addition, you have to think about kind of where the nucleophile goes, okay. So more substitute carbon or kind of last substitute carbon, kind of we call kind of Markov-Nikov, okay. But for the nucleophilic addition to aldehyde ketone, always go to this carbon, okay. Never go to kind of oxygen because this carbon kind of has a part positive charge, okay. So always go here, okay. So that's looks like make life easier, but unfortunately, okay. So in this chapter, okay. So the mechanism will be more complicated, okay. Will be more complicated, okay. So like I said, kind of some reaction push like maybe the 3 steps, okay. So all right. So here's kind of little bit the overview of the addition reactions, okay. So the mechanism, okay. So for the addition reactions, okay, so the nucleophilic addition reactions, okay, so can carry under either the acid condition or kind of basic conditions, okay. So we draw kind of one by one, okay. So in this case, you guys can have a little bit idea, okay. So so what's going on, okay. So for the mechanism, okay. So and then for all the kind of the condition, kind of all the reaction pretty much similar, okay. All right. So for the acid conditions, okay, so the pretty much happen kind of you have weak nucleophile, okay. So or normally kind of neutral one, okay. And then in this case if you want to add to kind of this carbonyl carbon here, you have to make it more active, okay. So in this case the oxygen under the carbonyl compound, okay. So the pick up protons, okay. So that's why kind of under acid conditions, okay. All right, so we have kind of positive charge on oxygen, okay. So that's the strong inductive effect, okay, make this carbon even more kind of the nucleophilic, electrophilic, okay, pulling electrons, okay. All right, and then the nucleophile coming, okay. So for the acid condition, normally speaking, kind of the nucleophile kind of just a neutral one or kind of very weak nucleophile, okay. Open CO bond, okay. right? And then finish addition, okay? Probably you have kind of take off the protons for nucleophile, kind of final neutral product, okay? So for the acid condition, okay, so normally kind of you have weak nucleophile, okay? And then you can also notice kind of when I draw the mechanism, kind of arrows kind of over double head, okay? So that's means kind of normally acid conditions, okay? So whole process kind of reversible, okay? Yeah, so that's it. Right. On the other hand, okay, so for the basic conditions, okay, so the nucleophile is much stronger, okay. Don't need any help kind of to open the single double bond, okay. Right. Right. So nucleophile directly coming in, okay. So for the basic the conditions, okay. So normally speaking, kind of nucleophile is kind of the negative charge kind of stronger one, okay. Right. And then that's here directly open single double bond, okay. Right, and then for the basic condition, normally speaking, kind of you also need to do some workup, okay, because normally speaking, kind of you get kind of leak charge on the oxygen, okay. So the workup, okay, pretty much use some kind of acid or water, okay. So protonated kind of this for negative charge kind of oxygen, okay. So that's workup. Okay. Yeah. And then give you kind of the final product, okay. So for the basic conditions, okay, so normally speaking, kind of the nucleophiles kind of strong and also pretty kind of the irreversible reactions, okay. Irreversible, okay. And how many lone pairs? Okay, let me see. Okay, so this one, okay. If you like, you can put your lone pairs back, okay. Yeah. Okay. All right. Okay, so before we started kind of kind of nucleophilic the addition reaction to aldehyde ketone, okay. So first kind of we need to compare aldehyde ketone kind of reactivity to nucleophilic addition reactions, okay. Right. So generally speaking, kind of aldehyde has kind of higher reactivity compared with ketone, okay. Right. Higher reactivity. So why is that? Okay, so that's showed here, okay. So so first kind of steric effect, okay. So for ketone has kind of two alkyl group, okay. Somehow kind of little bit steric hindrance, okay. So a nucleophile not easily attack kind of the center carbonyl carbons, okay. But for the aldehyde, okay, so only one alkyl group, one hydrogen pretty much won't take any species, okay. So that's make the aldehyde easy to open to nucleophile attack, okay. And another reason kind of electron factors, okay. So remember in the previous chapter we said kind of alkyl group kind of the somehow kind of weak electron donating group, okay. Can donate electron into kind of center carbons, okay. And if the donate electrons into center carbons can make the center carbonyl carbon not so electron poor, okay. So it's not so kind of electron deficient, okay. So if it's not so electron deficient, okay, less likely attacked by kind of nucleophile, okay. So nucleophile like kind of positive charge species, okay. And but for the aldehyde, okay, only has one alkyl group, okay. So not so strong kind of electron donating effect, okay. So in this case, center carbon has kind of not so kind of still kind of quite poor in electrons, okay, easily attacked kind of by nucleophiles, okay. Right. So that's one thing, okay. And then if there's kind of benzene, okay, conjugated with the aldehyde ketone, okay, so that will lower kind of reaction rate, okay. Here, okay. So not only benzene, okay, any aromatic compound, okay, so yeah, we use ARK. Okay. A reason for that kind of resonance effect, okay, so yeah, okay, so we draw here, okay. So there's kind of draw benzene as example. Right. And then you can draw kind of resonance structures, okay. Okay. So for the regular kind of aldehyde ketone, okay, so it's kind of you can only draw one resonance structure, okay. But for the benzene conjugated kind of aldehyde ketone, okay, so you can further draw kind of probably 3 more resonance structures, okay. And you can further kind of delocalize kind of this positive charge, okay. So that means kind of the node positive charge node the localized on the carbonyl carbon, and then it's the flow around, okay. So make this carbonyl carbon not so poor in electrons, okay. So less likely have kind of the nucleophilic addition reactions, okay. So that's the reason, just keep in mind, okay. So for you guys, just remember this order, okay. Normally aldehyde better reaction rate compared with ketone, and then the poorest one kind of the aromatic ketone, okay. Right. Here's the outline for the reaction of these chapters, okay. So we'll learn kind of addition of the hydride, okay. So it will reduce aldehyde ketone into alcohol, okay. Also we will learn kind of addition of the hydrogen cyanide, okay. So reduce aldehyde ketone into kind of cyanohydrin, okay. And then we will learn kind of two the carbon nucleophile addition reactions, okay. One called kind of Grignard reaction, one called kind of Wittig reaction. Also sometimes people call kind of VTC reaction, okay. Right, and then we will learn kind of the addition of the nitrogen kind of nucleophile, okay. So that the generate kind of imine product, okay. So it depends what's the nucleophile, okay. So if it's a primary amine, okay, generate kind of imine product, okay. If secondary amine, will generate kind of the enamine product, okay. And then there are kind of one extension reaction for this the addition of nitride nucleophile, okay, called kind of reductive amination, okay. So we will learn that later, okay. Right, and then in the end we will learn some kind of the additional alcohol, give kind of the acetal, okay, and some kind of the conjugated addition reactions, okay. Most the important reaction for this chapter kind of the 2 carbon nucleophile, okay, so Grignard reaction and the Wittig reaction, okay. And for the mechanism, okay, so just remember I said kind of the some reaction just stop at the first addition step, okay. So that's for the addition of hydride, also addition of hydrogen cyanide, okay. And those for the Grignard reaction, okay. So these 3, okay, so we will just kind of just give kind of alcohol pretty much, okay, or kind of the cyanohydrate, okay. But some reaction will to push the one more step, okay. Addition followed by elimination, okay. So that's Wittig reaction and also the imine formation reaction. These 2 will do kind of 2-step reactions, okay. And the most difficult ones kind of the acetal formation, okay. So this guy will do kind of 3-step, okay. So addition, elimination, addition, okay. So that's all 3 kind of finished, okay. All right, okay. So here we will study kind of the first the addition reaction is kind of addition of the hydride, okay. So hydride actually is kind of the H minus, okay. There's a lone pair electrons on the hydrogen and then here H minus, okay. So normally speaking, kind of we get over kind of H plus, okay, as proton, okay. So that's if the hydrogen kind of react with the some of the metal, okay. So then the metal had kind of poor electron negativities, okay. So hydrogen gain the electrons, then kind of hydride, okay. And then for the reaction of here, okay, so it's pretty straightforward, okay, just convert kind of CO double bond into kind of CO single bond and then OH single bond, okay, alcohol, okay. All right, so now we will learn kind of one by one, okay. This is hydride, okay. addition of the H minus. Okay. Right. For the general reaction for this addition of the hydride. Okay, so pretty much like this. Okay, so you have carbonyl or ketone. Okay, and H minus coming in. Okay. And then following kind of you may need to do some kind of the workup. Okay, so this one or maybe kind of directly kind of the oxygen minus pick up hydrogen from kind of the solvent. Okay, so that's give kind of final alcohol. Okay. Yeah, so that's the general reaction for hydride addition. Okay. And so that's just the one thing please write down. Okay, so this reaction kind of because hydride kind of very strong the nucleophile. Okay, and so normally this reaction just do it kind of under basic or kind of neutral conditions. Okay, you cannot use acid conditions. Okay, so because acid will react with hydride. Okay, so this reaction kind of irreversible. Okay. Yeah, basic and also irreversible. Okay. And here we will learn kind of two most common kind of hydride reagent. Okay, so one's kind of sodium boron hydride. Okay, another one's kind of lithium aluminum hydride. Okay, so so if we use these two reagent. Okay, so they actually have kind of quite different reaction conditions. Okay, so let me do it one by one. Okay. So if you use the sodium boron hydride, actually you can use kind of the water or kind of the alcohol. Okay. A solvent. Okay. And then the reaction pretty much just one step. Okay. So because after the addition of the hydrate, okay, quickly kind of the O minus pick up proton from water or alcohol. Okay. So for the hydrate reaction, okay, pretty much for the lithium ion hydride reactions, okay, pretty much you see something like this. Okay. Sodium boron hydride. Okay. So for sodium boron hydride, okay, so pretty much you see like this. Okay. Just kind of one arrow. Okay. So sodium boron hydride on top. Okay, and then the water or alcohol at the bottom. Okay. So once reaction is done. Okay. So that's it. Okay. But if for kind of lithium hydride. Okay. So lithium hydride kind of much strong kind of reduction reagent. Okay. So and those react with vigorously kind of with water or alcohol. Okay. So actually kind of if you pour some kind of water into lithium hydride, generate a lot of the hydrogen gas. Okay, and then a lot of bubble. Okay. So that's require kind of use some kind of inner solvent. Okay, inner solvent. Okay. So like ether. Okay. So to do kind of reduction reactions. Okay. And so after reactions, okay, so then kind of this negative charge kind of oxygen species. Okay, you have to do some workup. Okay, to finish kind of whole reactions. Okay, and so workup. Okay, so in this case when you write the lithium aluminum hydride the reduction reactions. Okay, so normally you do this. Okay, right. Step one. Okay. Lithium hydride. Okay. And if you like, you can list kind of solvent. But probably don't need list here. Okay. Step two. Okay, you do the workup. Workup you can use weak acid or some kind of just water. Okay, so that's the finish whole reactions. Okay, so so that's see a little bit of difference between these two reactions. Okay. Another just keep in mind. Okay, so lithium hydride need workup. Okay. Another kind of difference is kind of the sodium boron hydride has kind of better selectivities. Okay, so only react with kind of the aldehyde, ketone, and also imine. Okay, so what's imine? Okay, so we will learn it in future. Okay, so just keep in mind. Okay, these three kind of compound. Okay, and but for lithium hydride kind of has the much poor kind of selectivities. Okay, so not only these three. Okay, so aldehyde and ketone and imine. Okay. So for the lithium hydride can also react with kind of ester. Okay. and then corpuscular acid, okay. And also amide, okay. And even kind of the nitrite compound, okay. Right. So that means kind of lithium hydride kind of the much strong kind of reduction reagent, okay. Also kind of the hydride reagent, okay. So make the no selectivities, okay, no selectivity, okay. So later this chapter we will learn some kind of selective kind of reduction reactions, okay. So when you try to reduce kind of certain chemicals, okay, you have to think about kind of whether this reagent can reduce only one functional group or two functional group, okay. All right, and for both, okay, so lithium hydride and aluminum sodium boron hydride, okay, cannot reduce kind of the arcane, okay. So just CC3 bond, okay, CC bond, okay. So now this two reducing reagent can reduce kind of the arcane, okay. So for arcane reducing case, so we learn in kind of the chapter 11, we use kind of catalytic hydrogenation reactions, okay, hydrogen with kind of some the palladium, platinum, maybe some nickel, okay. So those please keep in mind, okay. All right. Here are some kind of example, okay. So so first one kind of try to use the lithium hydride reduce kind of aldehyde case. You can see kind of two steps case. So the first step case, lithium hydride in the kind of inert solvent, and second step case we do acid workup case. And then second reactions kind of use sodium boron hydride reduce this ketone in kind of alcohol case. So this one kind of you can see the pretty much just one step reactions. Okay, you don't need to do any workup. Okay, so because eventually O- pick up protons from kind of solvent. Okay. And last one's kind of still use lithium hydride and workup. Okay, so just show you kind of the selectivity kind of reduction. Okay, so selective reduction. Okay, so the lithium hydride only reduce kind of the CO bond. Okay, don't do anything to kind of the CC bond. Okay, so that's the pretty kind of the important thing. Okay. All right. Okay, so that's pretty much we done the lecture today. Okay.